We will conclude our study of vector valued functions by looking at motion in space. So we let r of t be a twice differentiable function of the parameter t that represents the position of an object as a function of time. So the velocity vector is v of t, which is simply r prime. The acceleration vector of the object is a of t, which is v prime or r double prime. The speed of the object is the magnitude of the velocity vector. So this is now a simple extension of motion that was studied in Calc 1 and Calc 2, except now we're applying it in multiple directions. So we're applying it with vectors. So we're going to try and break down the acceleration vector into two components. So recall that the unit tangent vector is r prime over the magnitude of r prime. So with the previous definition, we can write t as the velocity vector over speed. So this means that velocity is speed times the unit tangent. If we differentiate this, we'll get the acceleration vector is equal to the derivative of speed times the unit tangent plus speed times the derivative of the unit tangent. Now recall that the unit normal vector is the derivative of the unit tangent divided by the magnitude of the derivative of the unit tangent. And so this means that the derivative of the tangent is the unit normal vector times the magnitude of the derivative of the unit tangent. If we now substitute this piece into here, then we get acceleration is the derivative of speed times the unit tangent plus the speed times the magnitude of the derivative of the unit tangent times the unit normal. Now, if we recall that the curvature is the magnitude of the derivative of the unit tangent over speed, then we can write the magnitude of the derivative of the unit tangent is equal to the curvature times speed. And now just replacing this piece here with what we just said, this kappa v, we get the acceleration is the derivative of speed times the unit tangent plus the curvature times the speed squared times the unit normal. Here, the curvature we're talking about is the curvature of the curve that the particle is tracing out. So what discussion just showed is that the acceleration vector lies completely in the plane formed by the vectors t and n. The coefficients of t and n, respectively, are referred to as the tangential component of acceleration and the normal component of acceleration. So we then write acceleration as the linear combination a sub t times t plus a sub n times n. So again, this piece is known as the tangential component of acceleration, and it is defined to be the derivative of speed. This is known as the normal component of acceleration, and it is defined to be the curvature times the speed squared. So, real quick, let's say this is the curve that the particle is traveling around. So its tangential component of acceleration will be the acceleration that is tangent to the curve. So this is the magnitude of, just a sub t, right? Which is itself a magnitude. So it's not measuring direction. That's what this t does. This t is measuring the direction. The normal component is the component that is perpendicular to this tangential component. So it's typically towards the center of the curve. And again, this AN measures the magnitude of this component. Again, the direction is given solely by that N. Now, these formulas can be a bit tedious to work with, specifically this curvature one. Right? Curvature can be a pain in the butt to try and calculate. So let's see if we can find a simpler way of calculating these two components. We make note of A dot t, so acceleration dot the unit tangent. So using distributive law, we'll have AT times T dot T plus AN times N dot T. However, these two, as we just saw here, are perpendicular to each other. Right? T and N are perpendicular. So this dot product is 0. Since this is unit, their dot product is 1. And so we're left with just AT. Now if we do the same thing and try and do A dot N, again using distributive law, we'll get AN times N dot T plus AN times N dot N. For the same reason, this has to be 0. This here, again, N is unit, so the product is 1, and we're left with AN. So this gives us alternative formulas for A sub t and A sub n. However, it can still be pretty tedious to calculate the unit tangent and the unit normal vectors. So let's see if we can actually do better. Now, the unit tangent, remember, is velocity over speed. So we can write the tangential component as A dotted with V over speed. Well, we can treat this as over 1, or remember this is a scalar multiple, so we can pull that out to the front. Dot product order doesn't matter, so we can write the tangential component of acceleration is velocity dotted with acceleration all over speed. So now this allows us to calculate the tangential component only from the velocity and acceleration vectors. This is much better. Let's now examine the normal component. So from the figure over here, we see that the vectors AT and A sub n form a right triangle with hypotenuse given by A. So we have a right triangle of sides the magnitude of A sub t, t, which, since the magnitude of t is 1, and this is a scalar, we just have absolute value of AT, and the magnitude A sub n, again, magnitude of n is 1, this is a scalar, so we're left with the absolute value of A sub n, and the hypotenuse is the magnitude of A. So using Pythagorean theorem, the magnitude of A squared would be the absolute value of A sub t squared plus the absolute value of A sub n squared. And this gives the normal component of acceleration is the square root of the magnitude of acceleration squared minus the absolute value of the tangential component squared. Now, while this formula is certainly better, it still has one major drawback. It relies on the tangential component. What if we're only interested in the normal component? The normal component is also sometimes referred to as the centripetal component. So we would need a different formula. Now, remember that the tangential component was velocity dotted with acceleration, all over speed. So it would seem natural to say that the normal component would involve a cross product of velocity and acceleration. Let's now check to see if this is indeed accurate. So we take velocity cross acceleration. So velocity was speed times tangential times the unit tangent crossed with the acceleration. So we'll have v at t cross t plus v an t cross n. Now any vector cross itself is 0. So we're left with v a sub n t cross n. Now take the magnitude. So the magnitude of v cross a is the magnitude of this, which is the absolute value of VAN times the magnitude of t cross n. But this magnitude here is given as the magnitude of t times the sine of the angle between them. And since t and n are perpendicular, that angle is pi over 2. Each of these are unit, so they each have magnitude of 1. Sine of pi over 2 is also 1, so we're left with v a sub n. To solve for a sub n, just divide by speed, and we find that the normal component of acceleration is the magnitude of the cross product of velocity and acceleration, all divided by the speed. So in summary, we have 3 formulas for calculating the tangential component. It is either the derivative of speed, the acceleration dotted with the unit tangent, or more commonly, velocity dotted with acceleration, all divided by speed. And we have 4 formulas for calculating the normal component. The curvature of the curve times the speed of the particle squared, acceleration dotted with the unit normal, the square root of the magnitude of the acceleration squared minus the value of the tangential component squared, or more commonly, if you don't want to find tangential first, the magnitude of velocity cross acceleration all over speed. So here we have a particle. It moves in a path given by this vector parameterization, where t measures the time in seconds and distance is measured in feet. We want to find the tangential and normal components of acceleration as functions of time. So the first thing we need to do is we need to find the velocity and acceleration vectors. So velocity, remember, is just r prime. So we get 2t, 2, 6t minus 3. Then we want to find acceleration, which is just the derivative of velocity. So it's 2, 0, 6. Next up, we need speed, which is just the magnitude of velocity. So it's the square root of 4t squared plus 4 plus 36t squared minus 36t plus 9. And that simplifies to 40t squared minus 36t plus 13. So tangential component, remember, is v dotted with a all over the speed. So we get 4t plus 0 plus 36t minus 18 all over this square root. And so the tangential component of acceleration as a function of time is 40t minus 18 all over the square root of 40t squared minus 36t plus 13. We now just need to find the normal component. Now, since we already had defined tangential, we can just use the first formula for normal. So we'll need the magnitude of acceleration, which is the square root of 4 plus 36, which is 2 times the square root of 10. So if we now square this, it's just 40. So the normal component, square root of the magnitude of acceleration squared minus the absolute value of the tangential squared. So it's 40t minus 18 squared all over 40t squared minus 36t plus 13. And now this is going to be pretty intensive algebraically. So this will become the square root of 40 times 40t squared minus 40 times 36t plus 40 times 13, then minus 40t squared minus 40t times 36 plus 18 squared, and that whole thing is over 40t squared minus 36t plus 13. Now, we have a 40 times 40t squared, so that'll be 40 squared t squared, which is what this piece here is, so these two terms can drop out, thankfully. This is a 40 times 36t, this is a 40t times 36. They're going to be the same, except my deepest apologies. This should be positive, this should have been negative, right, because of this minus here. So sorry about that. Now they'll drop out, and what we're left with is the square root of 40 times 13, which is 520, minus 18 squared, which is 324. That'll be over 40t squared minus 36t plus 13. So we have the square root of 196 over that. And the square root of 196 is 14, so therefore our normal component of acceleration is 14 over the square root of 40t squared minus 36t plus 13. We will conclude this lecture by looking at projectile motion. So for this discussion, we are going to ignore air resistance of any kind. We define the positive y-axis to be upwards and the positive x-axis to be forward motion. Now, the effect of gravity is always downward. So a force due to gravity would be negative mg j hat, where remember this little g is the acceleration due to gravity, which is about 9.8 meters per second, or about 32 feet per second. So the acceleration, for projectile motion is simply negative g j hat. We now want to solve for position. Well, a is equal to v prime, so v would be the integral, the antiderivative of acceleration. So it's the antiderivative of negative g j hat, which is negative gt j hat plus some constant vector. Call it c1. Now, if the object is given an initial velocity of v naught, then plug in t equals 0 up here, we'll get v naught is simply c1. And so the velocity vector is given by v naught minus gt j hat. However, velocity is the derivative of position. So r would be the antiderivative of v. So we get the antiderivative of v naught minus gtj, which is v naught t minus gt squared over 2j plus some other constant, called c2. Now, if the object has an initial position of r naught, again, we plug t0 up here, and we'll get 0, 0, so r naught is simply c2. And so the position vector for projectile motion is r naught plus v naught t minus gt squared over 2 j hat. If we now suppose that the object is thrown upward from the origin at an angle of theta to the horizontal with an initial speed of v naught, then r naught is the zero vector, and we can rewrite v naught as v naught cosine theta I plus v naught sine theta j. If we plug these into here, then we get r of t is v naught cosine theta I plus v naught sine theta j t minus gt squared over 2j. Combining the I and j components, we'll have v naught t cosine of theta I plus the quantity of v naught t sine theta minus gt squared over 2 j hat. This is known as the equation of projectile motion. I have no examples on this. Typically a problem, you'll know speed, you'll know an initial speed, and you'll know the angle it makes. So just a simple matter of plug and chug. And so that will conclude our study of motion in space, and that also concludes our study of vector valued functions.